So, yeah, regarding this exercise 8, I know a few people were gone last week, and if that's the case, if you can just remind me today, I don't mind, if you have a couple extra days to finish up the exercise. I'm not going to let it go maybe more than a couple days, though, because it starts to take away time from this week's exercise, and if that happens more than once, you kind of get in a bad situation pretty quickly in terms of having to do too much in too little time. So yeah, for those who were gone, we'll have plenty of time to work on the exercise for today here in class. So when I'm just around, remind me that you were gone so I don't forget. And well, actually, maybe it's better even than reminding me to tell Yorina, because she's the one who's doing the grading, so she needs to know who gets an exception if they're late versus who doesn't. So there's that, and otherwise for exercise 8, I know in the past this course has been taught on Wednesdays. This year it's on a Monday, and a lot of times people liked being able to get some help after the weekend when you've maybe spent a little bit more time trying to finish the exercise. So I extended the deadline for exercise 8 until midnight today. So if you have any last minute questions, I can help with those, and Yorina can help with those while we're here. And I think for the future exercises, I'll basically just do the same thing. They'll be due at midnight on Mondays rather than at the start of class on Monday. So please don't wait until Monday to start working on it. But if you have any kind of last minute questions, you're almost finished, then I think it's fair to give you guys one more chance to get some input before the deadline. So Slack hasn't been super active. There's been a few questions there, but you can always post things there too. Yeah, and if you have questions about the exercise 8, we'll have time after the lesson today, so you're also welcome to ask those kind of questions then. And otherwise, let's go not here, but to our course. Here to our lesson for this week. So this week we're on to talking about things like goodness of fit calculations and least squares regressions. We're basically talking about comparing data to some kind of model. And the model in this case could be simply a linear fit to the data. But essentially we want to have some way of comparing a prediction and some data. And the lesson I think you'll see is quite short, and conceptually it's probably not too terribly challenging, but it will take a little bit of time with the code to sort of get things working, I suspect. So regarding goodness of fit calculations, I don't know if you guys have ever done anything like this, but essentially when you have some measurement like we saw last week, you usually report the measurement with some perhaps mean value plus or minus a standard deviation, whatever, some best estimate of the real value plus some uncertainty on the measurement. So you can see that kind of picture here of some measured age that's shown in blue with its error bar. And you guys made plots like this for exercise 8, so probably you saw things like this. Maybe your error bars didn't have the ends on them. That's a philosophical discussion for another time. But in this case, we have our measured age, and then we have in the little white boxes 2 predictions. So this could be from some very fancy numerical model, or this could just be some, could be a guess for what you think the age is. Doesn't really matter. The question is, when we compare this prediction to the measurement, how do we know when the two are equivalent to one another? So how do we know when our prediction fits the measurement? And of course you can see that visually pretty easily here, that in one case the predicted age falls within the uncertainty in the measurement. So if we can say nothing more than we know the value is somewhere within this range, then we could say that this prediction and the measured age are statistically equivalent to one another. They're basically equal to one another. Even though the mean might be different than this prediction, we know that these two are basically the same, whereas out here this predicted age in this example is outside the error bar, so we can say that these two perhaps are not equal to one another. And I guess that concept is probably not mind-blowing, right? You guys sort of understand that pretty intuitively, yeah? The thing is that you don't often have this picture when you look at age data sets, because maybe you're dealing with hundreds of ages, and you could go through on a plot and look at every single one of the measured ages, its uncertainty, and how some prediction compares to that measurement. But we can do a little bit better with some rather simple equations. And so in this case, that's the point of this goodness of fit part of the lesson. We're going to deal with a case where we just have point values and making a simple calculation for determining when the value is within the uncertainty of the measurement. And so here is what's called, if you want to sort of say the fancy name, the weighted sum of the squared errors for this equation, or it's often called chi-squared value. It's basically an equation where you sum up the difference between the mean value and the observed, or the estimated value, the prediction, and then you divide by the uncertainty squared. So here, O would be some measured age, or an age that you've determined from, uranium lead age that you've gotten from a lab or whatever. E is the prediction. So this is the blue circle, and this is the white square. Take the difference between the two and square it, and then you divide by the standard deviation squared. If you go back up here to this figure, and I guess I can kind of keep these two in the same view, essentially what we're doing is just, if the difference between this value and the mean is smaller than the uncertainty, we should expect that this statistical value should be less than 1 for a single age. So does that make sense to you? Yeah, if you take the difference between these two, it's going to be some small value, and if this is your uncertainty, if you divide by that uncertainty that's larger, then it should be a value that's less than 1. If they're exactly equal to one another, it should be 0, because the difference between the predicted age and the measured age would be 0 in that case. So that's what we're dealing with in terms of an equation. That's kind of spelled out here. So if the prediction and the data are exactly equal, you get a value of 0 for this chi-squared. And if, for instance, this predicted age sat out here at the end of the error bar, so it was exactly equal to 1 standard deviation from the mean, then you'd get a value of 1 for a single age in this equation. Now you'll notice again, this is this sort of sigma notation here. So this is a summation. So if you have more than one age, that value could be larger than 1, even though maybe you're on average falling within the uncertainty in the measurement. So that's the gist of what the equation is meant to do. There's a few cases that are described here in the lesson online, so if this doesn't make sense to you at the moment, hopefully if you read through the description here, it will make a bit more sense. As I mentioned here, if you sum up these values, and you could have cases where even though you fall within the uncertainty in the measurement, you get a value greater than 1. This is actually a little bit of a difficult equation to know right away whether or not you have data that fall within the uncertainty of the measurements or not. So there's another form of it that's shown in the sort of lower part of the lesson, where all we do is you just multiply by 1 over n, where n would be the number of ages you have summed together. By doing this, essentially what you do is you divide out the number of ages such that with this equation, a value of 1 or less tells you that on average you're within the uncertainty of your measurement. And a value of greater than 1 tells you that on average your prediction is outside of the uncertainty in the measurement. The reason that works is basically, it's probably quite simple to understand here. like I said with this case, let's say we have 10 ages, and all of them are 1 standard deviation away from the mean. When we take this summation here, then we would have, in this case, 1 divided by, or basically, this would be the standard deviation squared divided by the standard deviation squared, right? If the difference between these two is equal to the standard deviation, then if you divide standard deviation by standard deviation, you get 1. If you do that for 10 ages, you get a value of 10 for this equation. So that value of 10 might look like a bad fit to your data, even though you're exactly within the measurement uncertainty. Here, all you do is you take that value of 10 that you would calculate and you multiply by 1 over 10 because you have 10 ages, and that gives you a value then of 1. So I would not say that that verbally describing equations is a particularly effective way to teach you about them. But that's how the equation works. I'm kind of looking at you, and it sort of seems like this is somewhat understandable, and in some cases you're probably going, why the hell are we doing this? But anyway, the point is that this allows us to come up with some number that tells us how well we fit our data. So we can see it graphically, but if you have hundreds or even thousands of ages, doing this graphically just doesn't make any sense. So that's where this kind of goodness of fit calculation becomes helpful. In this case, we're dealing with age data, but you could very well be dealing with, many other types of data. I mean, essentially, you could put whatever you want down here on the bottom axis. As long as it's something you can measure and something you can estimate, then age is kind of useful because we're geologists. That's often one of our big concerns, but it could be slope angle of stratovolcanoes or whatever. I mean, you could come up with anything you want to put there. But you can use the same kind of statistical approach this way, as long as it's point values, not some kind of continuous distribution. There are statistical things for that too, but it's a little bit more complicated, so we're going to forego doing that. So yeah, any questions about this idea in terms of concept? It's not a really hands-on kind of Python type lesson today. It's just I'm going to walk you through the introduction to the problem and then turn you loose to work on the exercise. But okay so far? Yeah.
I think the standard deviation is for a group of data, but the O and E is for the individual data. So I think maybe in the equation the standard deviation is it's not changing.
Yeah, that's right. So the idea here is that, so last week you guys calculated standard deviation values for like a list of individual measurements that were made. And the assumption here is that what we're using for the observed age is the mean from that, and then its standard deviation. But we might be comparing then many samples. So if we have, let's say, a few ages at one sample location, and we calculate the standard deviation and the mean for those measured values from a single sample, this statistic would be used then to take multiple different samples from different locations, for instance. I don't know that that made the picture particularly clear, so let me say it a different way. If we go out somewhere out here and collected rock samples, and let's say we collected 5 rock samples from somewhere in the Kumpula campus, and we just wanted to date them. Oftentimes, when you measure something like the uranium-lead age or some age measurement that you make on the rock sample, you might date something like 5 minerals from one rock sample, because there's a little bit of uncertainty in the dating, and sometimes there are, there's a bit of natural variability in geological data. So when we take these measurements, oftentimes, like what you guys did last week, those were rock samples that were collected. Each one of the sample names you had was from one location where a sample was collected, and then there was something like 2 to 6 ages that were measured on minerals from that rock sample. With that, you can then get a mean age and a standard deviation for that one rock sample that was collected. So like if we did that out here somewhere on the Kumpula campus, we'd have 5 samples, and each one of the rock samples would have a mean age and a standard deviation. Does that make sense? Because I know you're not a geologist, right? So part of that might also be kind of confusing terminology between a statistical sample and like a rock sample that we collect out somewhere in the field. So anyway, normally what we would have is we'd have some rock sample where we've dated a certain number of minerals, and that gives us a mean age and an uncertainty. This statistic then is meant to be used to take samples from different locations, for instance, or multiple samples at the same location and compare them to some prediction. So in this case, we would have perhaps 5 mean ages, and then each one has its own standard deviation. So it's a good question, actually, because this does get a little bit confusing. It's slightly different than what we did last week in terms of how we're treating the age data. Now we're just dealing with the mean and the standard deviation, not the individual measured ages. We could do that as well, but in that case, then we'd have to consider the precision of the piece of equipment that's measuring the age, and that also could be a bit challenging to estimate. Can be done, but it's just a little bit more involved. So anyway, any other questions about this kind of concept of goodness of fit? All right, so the other thing that we're going to handle today is what's called least squares regressions. Probably if you've used Microsoft Excel, you've done this fit or add trend line thing where you just have some scatter plot and then you add the best fit trend line to it. Essentially, that's what we're going to calculate. And the whole point of doing the exercise is just to kind of give you some idea of how this works, because again, for me at least, it was always just kind of a black box. I could click the button to add the trend line, but I didn't really know what it meant or how it worked. So, in this example of the figure that's shown here, this is the temperature of magmas erupted as a function of their silica content. And there's some linear fit here between these 4 points of data. This isn't probably going to happen in nature, but in the textbook, this is how things look. So the point is we have these 4 combinations of points where we know the temperature and the weight % silica, and then we can fit a line through there. And you'll do this in the second part of the exercise for today using climate data instead of temperature and weight % silica, but it's the same kind of general idea. Of course, we have the equation for a line, and there's lots of different forms than this. I don't actually normally write an equation for a line this way. You guys maybe don't write an equation for a line ever, but this is the form that's I've used here because it comes up in how to do this least squares regression below. So the point is that you have some position y, so this would be a position on the vertical axis here, and you've got an intercept where this line would cross the y-axis at x equals 0, and then the slope of the line b. So a is the intercept, b is the slope, and those things probably, at least you would have learned at some point. You might not use it often, but this is something probably from high school math, if maybe even before high school math. So you may have to go back in your memory a while, but anyway, we have this equation for slope of the line, and we have ways to sort of estimate that as shown in the equation here. So if we have some true value that we know, we can estimate the true value based on if we know the intercept and the slope of the line. So essentially, we can put this line in here by just knowing these point values here. And that's the concept of what we're going to do. So there are descriptions of this linear regression stuff, or least squares regressions, in great detail that you can find, for instance, in this textbook that I've referenced here. I think it's a fairly accessible explanation, but it does involve a couple pages of math. So it's all algebra, so it's not super difficult math, but it's just, you got to get through it if you want to fully understand this in great detail. For us, all I'm going to do is give us the things we need to know to be able to make a plot of one of these trend lines with a set of points. And so we need to be able to calculate from our points the value of A, so that's going to be the y-intercept, so where we cross the y-axis at x equals 0. And this is a function of summing up the values of x and y for the data that we have here. So for each one of these points, we have its x and y coordinate. And if we sum up various combinations of those things, as is done here, that will give us the value of the y-intercept on the plot. Same thing goes for the slope, so you can get that from this equation for the line B here. Since we're not going to go into this in detail, and frankly, I'm not prepared to explain the kind of full derivation, you'll just maybe have to take my word for it for the moment. But we can get our slope and our intercept pretty easily here, and then we have to have this delta term that's in the denominator of both of these equations that basically just depends on some values of x summed in various ways. So with those combination of things, we can get the y-intercept and the slope for this regression line for any number of points. Okay, it doesn't work if you have 0 points. And I guess in the case of 1 point, I don't know whether this would work either. I guess probably not, because it won't be defined with only 1 point. But if you have more than 1 point, this equation should work to give you the trend line. And in this case, we're assuming it's unweighted. So I don't know whether that means much to you, but the point is we're not considering the uncertainty in the measurement in determining where the trend line fits through the data. You can do that, of course. You can say that the points that have a smaller uncertainty should make the trend line be closer to them, and points with a big uncertainty, maybe it's not as important, the trend line's close. But again, that involves a bit more algebra, and it, I think, just kind of complicates things in a way that we don't need to do right now. If you're curious about that, I do believe this is explained in this Taylor textbook, and I think there's copies of the textbook in the library. Or if you're willing to be not dishonest, but browsing the internet in places that maybe you shouldn't, you can find copies of books like this online as well. So I wouldn't suggest doing that, but I just say that I believe it's possible. Anyway, that's the point here for what we're going to do in the exercise part 2 today. We're basically going to have some point data. We're going to fit a slope line through there, and then you'll say a few things about what the slope and things like that indicate. So again, any questions about this in terms of concept or, well, anything, I guess, about this fitting regression line thing? I mean, again, you've probably done it before, just turning on the fit trend line thing in Excel, but this actually maybe gives you a bit more insight into how the calculation actually works when you do that in Excel. If there aren't any questions, then we'll go here. So exercise 9 should be up, should be accessible. I saw at least one person cloned the repository using the GitHub Classroom link earlier. So I'm going to open the exercise. Should see something like this. And yep, it's got the right due date and stuff like that. So the exercise is basically on comparing data to predictions. And we were going to do it two different ways, as you might imagine. We had two things in the lesson. We're going to do two things in the exercise. The first one is we have a broken Python script here to compare some age data to predictions from a numerical model. So you have both the predictions from the model and the age data, and all you're going to do is just calculate this goodness of fit statistic. I guess the age data file is here. It looks like this. Probably doesn't really mean a whole lot to you to look at the data file in this way, but I'll just highlight a couple things. We have longitude, latitude, elevation, and then we have the measured age, so that's going to be the mean age for one of the samples, standard deviation, and predicted age. So this would be something from the numerical model. So you have all the columns there, and all you want to do is just go through line by line, essentially, and compare the observed age and the predicted age and divide by the uncertainty in each one of those measurements. So you'll do that using this chi-squared statistic, the one that does divide by 1 over n, and will allow you to then see, on average, do you fit within the uncertainty of the data or not in this case. So you'll go through and you'll see the spot in the script. I guess I can show you that as well. So this is the Python script. Again, it's broken, so there's some stuff that's here, like importing NumPy and Matplotlib. I've done that for you. But you need to fix the way in which the data file is read in. We're doing it with the NumPy form of reading a text file this time. So we saw that last week, I believe. And so you have to add something here to make it skip over the header. I basically flagged in here all the spots where you have to fix something. And I think in total there are 6. So you go through and fix the script. The comments kind of tell you what to do, but don't tell you how to do it. So that part's up to you. I'm not going to can't do both parts. You won't learn anything that way. So you'll work your way through that, calculate this goodness of fit statistic, and at the end, then you make a plot of the measured values with their error bars and then the predicted ages from the numerical model. You plot those two things together so that you have your statistical number that comes out, and then you can also see what the data look like and how they compare. So that's problem 1, and then there's a couple questions at the end just about basic stuff related to how well the data fit. That sound all right so far? Yeah? Problem 2 is it's a little bit different version of what we did last year, so hopefully I don't have any sort of mistakes in here in the description. But here, what we want to do is, well, as I've hinted, detect changing climate. And we're going to do that using the climate data we've been working with for exercises 6 and 7 in the GeoPython part of the course. So those are back to haunt you again. In this case, what we want to do is, instead of looking at the temperature anomalies like we did in exercises 6 and 7, where you calculated these kind of the diff value and plotted it in different ways, here what we want to do is just take the actual regular temperature values and plot out the temperature values and put a trend line through there. So instead of looking at the anomaly, we're just going to fit a regression line through the temperature data. And well, what we can see from that is if the slope is positive, it should tell us that the temperatures have been increasing on average. If the slope is negative, they've been decreasing. And if it's 0, then that means the temperature on average hasn't changed over the time period we're considering. So it's a slightly different way to look at the same kind of data that we did before. And there are kind of good and bad things about both approaches. So your job here is to basically create a script where you do something you've already done in exercise 6 and 7, where you calculate the seasonal average temperatures, and then you calculate the standard deviation in the seasonal temperatures. So you remember that you had monthly temperature data, and you combine those into seasonal values for winter, spring, summer, and fall. Since you have 3 months that go into each one of those bins, you can also calculate what the standard deviation in temperature is for that season. And so that's what you're going to do as an additional column. You can do this in pandas if you want. If you're comfortable working in pandas and you want to do it in a pandas data frame, you can. If you want to do it in NumPy, that's perfectly fine too. There's more than one way to solve this problem. I did it the pandas way when I tested the exercise, and that was not too bad. But I'll probably do it the NumPy way while you guys get started, just so that I have a sense of how that works. But the point here is that you'll calculate seasonal averages and also standard deviations, which we didn't calculate before. And we're only going to do it for summer and winter. You can do this for the spring and fall if you'd like, but the last, third point here is plotting the data. And if you plot all 4 seasons together on one plot, it gets kind of busy. So if you're curious, you're welcome to do that, but it's not required. We'll just compare summer and winter. So you'll calculate these values, then you're going to calculate the slopes and intercept values for this linear regression. So basically using the stuff from the lesson, we'll calculate the trend line through this data for the entire time period, so from 1953 to 2016, and then separately for just the last 20 years. So we'll look at the temperature change trends over 2 different time periods. Then you'll make a plot, and you're going to plot the values for each seasonal temperature with their uncertainties, and then you'll put your trend line as well. And so you'll have 2 plots, of course, one for the entire time period and one for just the last 20 years. And then, your plot should have the normal stuff, axis labels, title, legend, things like that. Things that, that should be there for any kind of plot. So, yeah. For this problem, you're welcome to kind of go at it either working with your code from exercise 6 and 7 if you want to keep using the code that you've already started working with. You're welcome to do that. Or I have supplied a seasonal data file. So this should have been the thing that was output from your script from exercise 7. So if you're not confident that you did exercise 7 correctly, we're probably not going to mark you based on whether or not the data you plot is completely right so much as whether you have all the things that need to be in the plot. But you have this file you can work with if you want. So if you prefer to start fresh with a new script and just load this file in, you can do that. So it's just got average temperatures in Fahrenheit, average temperatures for each month in Celsius, and then this, which you don't need, is the temperature anomaly column. So you won't need that for the exercise today. So that's the job for this week. And there are some hints. Just a couple things here that might be useful about calculating summations. You had to do this already last week, so but in case you're looking for some additional hints here, there are some cases like where you can't use the sum function in Python. So this is an example of summing numbers that are squared. You can't do that with the sum function very easily in Python. And then there's just a little hint here about shorthand notation for when you're adding values to some variable. There is a short way to write that. It's kind of thing where you have like number equals number plus 5. Well, it's exactly what's shown here, that you can write number plus equals 5, and that's just saving the value of number plus 5. So it's just a shortcut for when you start to get long lines. Yeah, I don't know. I think that's most of the story for this week. So are there questions about the exercise?